Good morning, everyone. In today's lecture, we are going to learn about neural language models. I'm Arghya Kundu, and my email ID is arghyak@yorku.ca. If you have any questions regarding NLP or deep learning, please drop me an email. So the first topic we are going to learn today is how to apply feed-forward networks to NLP tasks. Then we are going to talk about how to train neural nets. We're going to give a brief overview of the subject. And finally, we're going to learn computational graphs and backward differentiation algorithms. So let's get started. So let's consider two simplified sample tasks. The first is the text classification and the other is the language modeling. Now, state-of-the-art systems use more powerful neural network architectures, but simple models are useful to consider. So in this lecture, we're going to use the simple models. In this section, we will look at classification tasks like sentiment analysis. In the next section, we'll introduce neural language modeling. So in the sentiment analysis, we could do the exact same thing using a logistic regression. The input layers are binary features as before, and the output layer is either 0 or 1, that is positive or negative. The input element xi could be a scalar of features like the count of the positive lexicons, the count of the negative lexicons in the document. If there is a no in the document, that is the sum of the no's, or otherwise the count of the first and the second pronouns, the count of the number of times an exclamation mark is there in the document, or the log of the word count of the document, or any other features that you might think of. Now, a two-layer feed-forward network can be thought of a logistic regression having the same architecture as the logistic regression, but having a separate additional layer before the output and after the input. That is, just by adding a hidden layer to the logistic regression, we can think of it as a two-layer feed-forward network. So in the hidden layer, that is the one layer that we just added, nonlinear interactions between features can be made, which may or may not improve performance. Most neural NLP applications do something different, however. Instead of using hand-built human-engineered features as the input to a classifier, we draw on deep learning's ability to learn features from the data by representing words as embeddings, like the word to wake or the glove embeddings. There are various ways to represent an input as for classification. One simple baseline is to apply some sort of pooling function to the embedding of all words in the input. For example, for a text with n input words or tokens, say W1 to Wn, we can turn this into n embeddings E1 to En, each of dimensionality d, into a single embedding of dimensionality d by just summing the embeddings, that is by taking their mean. There are various ways to represent an input for classification. One simple baseline is to pooling some sort of pooling function or embeddings, and or by taking taking their mean or taking the highest frequent embedding in highest frequent number in each of the dimensionality of the embedding. In practice, we want to efficiently classify an entire test set of n examples. We do this by vectoring the process, just as we saw with the logistic regression. Instead of using for loops to go through each example, we will use matrix multiplication to do the entire computation of an entire test set at once. First, we pack all the input feature vectors for each input x into a single input matrix peak of x. With each row I, a row vector consisting of the pooled embedding for input examples x. The idea of using word-to-vec or glove embeddings as our input representation, and more generally, the idea of relying on another algorithm to have already learned an embedding representation for our input words. This is called pre-training. Using pre-trained mod embedding representations, whether simple static word embeddings like word-to-vec or much more powerful contextual embeddings, which we will introduce later. Now, text comes in different sizes. In this example, we assume the text size length to be 3. And this is actually kind of unrealistic. There are solutions available which are more sophisticated or simple, like make the input of the length of the longest review, that is, if shorter, then pad with 0 embedding. If it's bigger, then truncate it with your to get longer reviews at test time, or create a single sentence embedding the same dimensionality as the word to represent all the words. That is, as I talked earlier, to take the mean of all the word embeddings or to take the element-wise max of all the word embeddings. For each dimension, pick the max value for all words. Now, what if you have more than 2 output classes? In this example, we talked about sentiment analysis for the positive and the negative. But what about if there is a neutral class also there? So what we can do is we can add more output units to one in each of the class and then use a softmax layer to give the probability distribution of each of the output layers. Language modeling. It is a calculating the probability of the next word in a sequence of given some history. We have talked about the n-grams based LMs, but neural network LMs are far outperform n-grams language models. State-of-the-art neural network State-of-the-art neural language models are based on more powerful neural network technologies like the transformers. But simple feed-forward neural language models can almost do as a very good example. State-of-the-art neural language models are based on more powerful neural network technologies like transformers. But simple feed-forward LMs can do almost as well. Now, take the task of predicting the next word, WT. Given some prior words, WT1 minus 1, WT minus 2, WT minus 3. Now, we are dealing with a sequence of arbitrary length, right? So, the solution is to use a sliding window of fixed length. Here is a sketch of the simplified feed-forward neural language model with n is equal to 3. We have a moving window of time at time t with an embedding vector representing each of the 3 previous words. That is the words t, w of t minus 1, w of t minus 2, and the w of t minus 3. These 3 vectors are concatenated together to produce x, the input layer of the neural network, whose output is a softmax with the probability distribution over words. Thus, y42, the value of the node 42, is the probability of the next word WT being v of 42. That is a vocabulary word with index 42. So let's take an example. The training data, we have seen that I have to make sure that the cat gets fed, but the LM has never seen this particular sequence of word called the dog gets fed. The test data in the this is the test data which says I forgot to make sure that the dog gets dash. Now we are tasked, the LM is tasked to predicting the next word, that is a dog gets dash. If it's an n-gram LM, it cannot predict fed because it has never seen the prior words dog gets in its training data. But if it's a neural LM, it can predict it because neural LMs can use similarity of the cat and dog embeddings to generalize and predict fed after dog. So we've seen how simple feed-forward networks can be applied to various NLP tasks. Now, how do we train neural networks? Let's start with an overview. The intuition of neural net training is the forward computation of the loss and the backward computation of the weight updates. Given an input X, we run a forward pass through the network, computing the system's output Y hat. Then we compare Y hat to the true answer Y to get a loss for this example. Then we do a backward pass through the network, computing the gradients we need to update the weights. So let's, for every training tuple xy, run forward computation to find our estimate y hat, run backward computation to update weights. For every output node, we compute loss L between true y and the estimate y hat. For every weight W from the hidden layer to the output layer, the weights are updated. For every hidden node, we assess how much blame it deserves for the current answer. And for every weight W from the input layer to the hidden layer, we update the weights. Let's next get an intuition from what we did for logistic regression. Remember our loss function for binary logistic regression? We would like to learn weights that maximize the log probability of the correct label P of Y given X. To turn this into a loss function, something that we need to minimize, we flip the sign. And then we can plug in our estimate of the probability from the sigmoid of the weights. And let's recall from the lecture on logistic regression how gradient descent works for weight updates. The magnitude of the amount to move in gradient descent is the value of the gradient of the weight loss with respect to W, weighted by a learning rate sigma. The higher or faster learning rate means that we should move W more on each step. The change we make in our parameter is the learning rate times the gradient. For logistic regression, we saw that the derivative of the loss function with respect to one weight W of J coming from input X of J. Now, where did that derivative come from? Using the chain rule, of course. Remember, the chain rule says that if we have a composite function fx of u vx, the derivative of fx is the derivative of ux with respect to vx times the derivative of vx with respect to x. Here's our neural unit, which is the same as a logistic regression. It's computing the loss as a function of y, which is computed as the sigmoid of the sum of the weights time values. If we want to do the derivative of the entire loss function with respect to one weight, Wi, we can compute this using the chain rule. The derivative of L with respect to Wi is the product of the derivative of L with respect to Y times the derivative of Y with respect to Z times the derivative of Z with respect to W of I. Now, how can I find the gradient for every weight in the network? These derivatives on the prior slide only give the updates for one weight layer, that is the last one. What about the deeper networks? There are lots of layers, right, with different activation functions. The solution is in the next lecture. Even more use of the chain rule and the computational graphs and the backward differentiation. We have seen an overview of the neural net training. In the next lecture, we'll see the details of computational graphs and the backward differentiation. For training a neural net with gradient descent, we need the relevant gradients for each weight, the derivative of the loss with respect to each weight in every layer of the network. But the loss is computed only at the very end of the network. How do we find these gradients for weights in the early layers? The solution is a method called error backpropagation or backprop in the neural network world. It turns out that backprop is a special case of backward differentiation, a method that relies on computational graphs. A computational graph is a representation of the process of computing a mathematical expression in which the computation is broken down into separate operations, each of which is modeled as a node in the graph. Consider computing the function L of ABC is equal to C of into A plus 2B. If we make each of the component addition and multiplication operations explicit and add names D and E for the intermediate outputs, the resulting series of computation is D is equal to 2 into B, E is equal to A plus B, and L is equal to C into E. We can now represent this as a graph with nodes for each operation and directed edges showing the outputs from each operation into the inputs to the next. The simplest use of computational graph is to compute the value of the function with some given inputs. Let's assume the inputs A is equal to 3, B is equal to 1, and C is equal to -2. We can walk forward and compute a value for D, then a value for E, and then a value for C. That is L is equal to coming as -10. The importance of computational graph comes from the backward pass, which is used to compute the derivatives that we'll need for the weight update. In this example, our goal is to compute the derivative of the output function L with respect to each of the input variables, that is delta of L by delta of A, delta of L by delta of B, and delta of L by delta of C. The derivative of delta L by delta A tells us how much small change in A affects L, while holding the others constant. Consider a composite function fx of is equal to u of v of x. The derivative of fx is the derivative of ux with respect to vx times the derivative of vx with respect to x. The chain rule extends to more than two functions. If computing the derivative of a composite function fx is equal to u v w of x, the derivative is du by dv dot dv by dw dot dv by dx. Let's now compute the three derivatives we need. Since the computational graph L is equal to CE, we can directly compute the derivative dl by dc. It will be E. For the other two, we'll need to use the chain rule. Those equations we have put them here on the top, thus require 5 intermediate derivatives, which are as follows. That is the dl by de, dl by dc, de by da, de by dd, and dd by dv. In the backward pass, we compute each of these partials along each edge of the graph, from right to left, multiplying the necessary partials to result in the final derivative we need. Thus, we begin by annotating the final node, that is dl by dl is equal to 1. Moving to the left, we then compute dl by dc and dl by de, and so on, until we have annotated the graph all the way to the input variables. The forward pass conveniently already will have computed the values of the forward intermediate variables we need, like d and e, to compute these derivatives. In the backward pass, we compute each of these partials along each edge of the graph, from right to left, multiplying the necessary partials to result in the final derivative. At each node, we compute the local partial derivative with respect to the parent, multiplying it by the partial derivative that is being passed down from the parent, and then it passes to the child. Thus, we begin by annotating the final node dl by dl is equal to 1. Moving to the left, we then compute dl by dc and dl by de, and so on, until we have annotated the graph all the way to the input variables. Of course, computational graphs for neural networks are much more complex. Here's a sample computational graph for a 2-layer neural network with n is equal to 0, n1 is equal to 2, and n2 is equal to 1. In order to do the backward pass, we will need to know the derivatives of all the functions in the graph. The derivative of the sigmoid function and the ReLU function is given here. The weights that need updating, those for which we need to know the partial derivative of the loss function, are shown in orange. So for the particular example x1 and x2, we would run the forward pass, assign values to each of our nodes, and then starting with this last node, we backwards pass. So this is how we do it. We use the log function, the log loss function, for computing the log loss error. And these are all the equations involved. Please pause here and take a look at this equation. For training, we need the derivative of the loss with respect to the weights in early layers of the network. But loss is computed only at the very end of the network. The solution is the backward differentiation. Given a computational graph and the derivatives of all the functions in it, we can automatically compute the derivative of the loss with respect to these early weights. Thank you.